Dear students, today we are going to learn how to synthesize para-nitroacetanilide. The general advisory about this synthesis is that this video is for educational purposes only and all safety precautions were taken during the demonstrations. The waste generated during the experiment was properly detoxified and safely disposed. The students are advised to follow all safety measures and perform the experiment under the supervision of their guide, educator, or trained professional only. Let's talk about the nitration reaction. Nitration is a common reaction which is an important reaction and is used in the synthesis of nitro compounds. These nitro compounds can be used as starting material for various essential commercially useful materials including drugs, dyes, explosives, etc. Here in this experiment, we will be synthesizing para-nitroacetanilide by the nitration of acetanilide. The principle behind the synthesis of para-nitroacetanilide is that it is prepared via nitration of acetanilide. The acetamido group, that is NHCOCH3, as you can see in this structure, is ortho and para directing. Therefore, when this particular compound will be nitrated, we are going to get a mixture of ortho and para nitroacetanilide. The acetamido group, being a bulky group, causes some steric challenge at the ortho function. That is the reason why para-nitroacetanilide is formed as the primary product, and upon crystallization from ethyl alcohol, para-nitroacetanilide crystallizes out while the ortho isomer, which is formed in minor amount, stays in the solution. So that is how you can separate the para and the ortho isomers of nitroacetanilide. The para-nitroacetanilide is obtained by nitration of acetanilide, and the chemical equation involved is we take acetanilide, it is reacted with the nitrating mixture, that is a mixture of concentrated nitric acid and sulfuric acid at a temperature below 20 degrees centigrade, and we get para-nitroacetanilide. The materials required for the synthesis involve acetanilide 5 grams, glacial acetic acid 5 ml, concentrated H2SO4 10 ml, fuming HNO3 2 ml, and ethanol for the recrystallization purposes. The theoretical yield of this reaction can be calculated as shown here. The amount of acetanilide that we have taken is 5 grams. Therefore, we can calculate the moles of acetanilide taken by dividing this amount from the molecular mass of acetanilide, which comes out to be 0.037 mole. As in this reaction, we are using nitric acid in excess. So here, the limiting reagent is acetanilide, and ideally 0.037 mole of para-nitroacetanilide should be formed. So the theoretical yield comes out to be 0.037 into 180.1 gram, that is the molecular mass of para-nitroacetanilide, which comes out to be 6.66 gram. So this 6.66 gram is the theoretical yield, and from this theoretical yield, the percent yield can be calculated. That is the yield which you obtain in the experiment divided by this theoretical yield into 100. The mechanism of this nitration reaction is that this para-nitroacetanilide is prepared through nitration reaction. So when it is treated with nitrating mixture, we are going to get a mixture of para-nitro and orthonitroacetanilide, and the orthonitroacetanilide is formed as the minor product. Since orthonitroacetanilide is much more soluble in alcohol, so para-nitroacetanilide can be separated through crystallization. It is a type of electrophilic substitution reaction, abbreviated as ESR reaction. Here, the electrophile nitro group will attack the para position in the form of nitronium ion, because the NHCOCH3 group is considered as an electron releasing group, and being an electron releasing group, it is ortho-para directing. So the various steps of the mechanism are: sulfuric acid is acted upon by nitric acid, which abstracts the proton from sulfuric acid and forms hydrogen sulfate and protonated nitric acid. And protonated nitric acid loses a molecule of water to generate nitronium ion, which is the electrophile of the reaction. This nitronium ion then approaches at the para position of this acetanilide and forms this particular cationic intermediate, which is losing proton to the HSO4 negative ion, forming H2SO4 and generates para-nitroacetanilide. The nitronium ion can approach the para position, forming the para-nitroacetanilide. It can also approach at the ortho position, in which case we obtain orthonitroacetanilide. So the overall mechanism can be shown in this single slide. Sulfuric acid acted upon by nitric acid, forming hydrogen sulfate, and this protonated nitric acid which loses water molecule forming nitronium ion, and the nitronium ion approaches either the para position or at the ortho position as shown in these equations, leading to the formation of the para-nitro and orthonitroacetanilide. So let us see how will we proceed for the synthesis of para-nitroacetanilide. We'll first of all take 5 gram of powdered acetanilide in 100 ml conical flask, to which we will add 5 ml of glacial acetic acid and stir the mixture with a glass rod. In the next step, we will take 2 ml of the fuming nitric acid in a test tube and cool it nearly to 0 degrees centigrade in a freezing mixture bath, which is nothing but a mixture of ice and salt taken in a beaker. Then we'll add to it 2 ml of concentrated sulfuric acid drop-wise with constant shaking and cooling, and our nitrating mixture is ready. Now, the remaining 8 ml of concentrated H2SO4 are added drop-wise to the conical flask containing acetanilide and the glacial acetic acid. Place the conical flask in a freezing mixture and stir the contents with a glass rod and cool them till the temperature becomes less than 5 degrees centigrade, and this temperature can be checked with the help of a thermometer. To the conical flask, we'll add the nitrating mixture prepared in the previous step drop-wise with constant stirring, and we will be doing this addition slowly, taking a time span of about 10 minutes, and we'll remove the conical flask from the freezing mixture and then allow it to stand at room temperature for about 15 to 20 minutes, and finally pour the contents of the flask over the crushed ice taken in a beaker, stirring it and then filtering off the crude product which is formed. As told earlier, the nitration leads to the formation of ortho as well as para products. So we need to obtain the para-nitroacetanilide. For that, we will be recrystallizing the synthesized compound. For that, we'll dissolve the crude product obtained in the synthesis in minimum amount of ethanol. We will warm this to get a clear solution. Then we'll filter hot solution immediately and cool the filtrate in ice. The orthonitroacetanilide will remain in the filtrate while the para-nitroacetanilide is obtained as a solid, and we will filter it. We will wash the product with cold water and dry the solid, weigh it and record its yield. So this is how the product will look like after recrystallization. The precautions to be taken while synthesizing para-nitroacetanilide involves these steps. First is that concentrated acids are corrosives and cause severe burns when come in contact with the skin. So we need to avoid the direct contact with the skin. Glacial acetic acid is a known respiratory irritant, so inhalation of its vapors should be avoided while using and should be kept under fume hood. Acetanilide used is toxic and can be absorbed through skin, so gloves should be worn while handling it. During the addition of nitrating mixture, the temperature should not rise above 15 degree centigrade. The various viva questions related to this synthesis are that why do we use glacial acetic acid? It is because it is a polar solvent and can dissolve acetanilide. Secondly, it doesn't pose the danger of competing substitution reaction because it is a poor nucleophile than nitronium ion. Secondly, why do we add the nitrating mixture dropwise? It is to prevent the dinitration forming the 2,4-dinitroacetanilide product. Why do we use ice bath? Because nitration is an exothermic reaction, so decreasing the temperature will favor the product formation. Further, it also aids in selectivity as the ortho and the dinitro products require higher energy, so the use of the ice bath is going to favor the synthesis of para-nitroacetanilide product. How to separate the ortho and para isomer? That we know by recrystallization, because there is a difference in the solubility in the ortho and the para product. Why no hydrolysis takes place during nitration? Because the reaction doesn't involve any heating and no water is being used, which is essential for the hydrolysis reaction. Why nitrating mixture is added to acetanilide and not vice versa? This is to keep the concentration of HNO3 to a minimum. And why para-isomer is the major product? That we have already seen in the mechanism, that it is due to the steric reasons. The approach of the nitronium ion at the ortho position is restricted due to steric reasons given by the acetamido group. Thank you very much.